not really being serious here, of course. This is Britain, so this must be Greenland. And you can pick up the coast of North America, starting maybe with the Gulf of Mexico and heading north. So all this ought to be Canada, and the North Pole ought to be here somewhere. But in fact, coming up round the back, we have South America. It's upside down, but this is South America, and there's the southern tip, right at the top. And in fact, however you tried to map the Earth onto a torus, you'd always get some sort of really drastic departure from reality, which is not surprising, you might say, because the torus is not the right shape. But the usual representation of the Earth's surface as the surface of a sphere is not exactly right either. The Earth is a little flattened at the poles. Yet in contrast with the torus, there's nothing really drastically wrong with this map. The reason for that is just what you feel intuitively, that the sphere is an acceptable approximation, but that the torus is really fundamentally different from the Earth's surface. In mathematics, it's the subject of topology, which captures that intuitive sense we all have that there are sphere-like surfaces which are all more or less the same sort of shape, but that these differ fundamentally from torus-like surfaces. That is, topology certainly distinguishes between the sphere and the torus, but it doesn't distinguish between the sphere and the Earth's surface. In fact, it doesn't even distinguish the sphere from any of these surfaces. It considers all these to be essentially the same. The advantage of this crude attitude towards surfaces is that it takes the enormous variety of surfaces we see all around us and reduces them down to a manageable set of classes. That is, we get a clearly defined list of all the topologically different classes of surface. In fact, as you'll see, the classification is based on just 3 very intuitive characteristics of surfaces. And that's what at least half of this course is about, the topological classification of surfaces. In this program, we'll give you an overview of how we classify them.
To make a start, let's be more precise about what we mean by a surface. It's what you would expect intuitively, essentially that a surface is two-dimensional. That is, if we take any point on the surface, then the collection of points within a small distance looks like a disk with a point at the center. And that's essentially the definition of a surface. It's locally disk-like. There are a couple of modifications, though. One is quite simple. If the surface has a boundary, like these cylinders, then for a point actually on the boundary, the collection of nearby points looks like a half-disk, with a boundary point on the edge. A second modification is one we've chosen to impose in this course. We insist that surfaces must be metric and compact. Metric, so that we can talk about distances, and compact, well, roughly speaking, that just excludes anything that's infinite, like the whole plane R2.
Now that we have our locally disk-like definition of a surface, I can explain the criterion we use when we lump surfaces together into a single topological class, like one of the 4 classes that we have here. You can see from this example that we intend to regard surfaces as being in the same topological class if we can get from one to the other by a continuous elastic deformation. For example, if this tetrahedron was made out of elastic, you could imagine gradually inflating it, first into this shape, and finally into a spherical shape. Let's concentrate on the full elastic deformation. It's one example of what we call a homeomorphism. And homeomorphism, I'll define it precisely in a minute, is the criterion we use when we classify surfaces topologically. If there's a homeomorphism between one surface and another, we regard them as being topologically the same. Otherwise, we regard them as different. Now, let me define homeomorphism properly. Consider a patch or disk on this tetrahedron, consisting of points which are close to this central point. when the tetrahedron deforms elastically into a sphere, this patch would turn into a similar disc-like patch round the image point. This illustrates the precise definition of a homeomorphism. It's a one-to-one map from one surface onto another, which is continuous. That is, for each point like this, points close to it are mapped close to the image point. And in addition, the inverse map has to be continuous. That is, if we map each image point on the sphere back to where it came from on the tetrahedron, then that map has to be continuous. Anyway, for the sphere and the torus, there is no homeomorphism mapping one onto the other. But how do we know that? How can we be certain that there is no really ingenious map which is a homeomorphism? Well, the course provides a foolproof method for determining whether two surfaces are homeomorphic. That is, for determining which topological class a surface belongs to. And that method is what the rest of this program is about.
The basic technique we use to study surfaces is to cut them up and flatten them. Take the torus, for example. If we cut along this orange band and then round this white band, we can flatten it out into a rectangle. Let me do that on this deformable copy. First, cut along the orange band. This arrow, which is now split in two, is to remind me how the torus was originally glued together. Now I can straighten it out into a cylinder. And now I have to cut it along this white line, which was originally this white circle. Let me do that on this copy of the cylinder. And that does it. Now, what's the point of doing this? Well, the rectangle I've ended up with is topologically the same as this object, a torus with two cuts in it. The homeomorphism between them is the deformation I just performed of opening out and flattening. So if you now imagine these edges are still being glued together, then what you've got is topologically equivalent to this with the edges glued together, which is the intact torus. And that's how you have to interpret this rectangle. In your mind, you have to identify the two white edges as a single edge and the two orange edges as a single edge. If you do that, then you can study the torus by studying the rectangle with these identifications understood on the edges. Now, if we can cut and flatten all our surfaces, we'll end up with flat rectangles or other polygons to study. And these will be easier to work with and therefore to classify than the original surfaces. Let's take another example, the sphere. If we cut the sphere from the North Pole to the South Pole, we can open it out and flatten it into a map like this. We've indicated the cuts by the coloured edges. In the northern hemisphere, this white edge is the 180 degrees east meridian, which is, of course, the same as the 180 degrees west, and the same for the red edges in the southern hemisphere. You can see how we could recover the sphere by bending these edges backwards and gluing them to give this join down the Pacific. So now we've seen that we can cut both the sphere and the torus and flatten them in such a way that the flat representation contains all the information necessary to mentally reconstruct the original surface. But the edge identifications are crucial. For the sphere, it's adjacent edges which have to be identified, whereas for the torus, it's opposite edges. By the way, I better point out that there isn't just one way of cutting and flattening these surfaces. For example, we've seen that the sphere is homeomorphic to the tetrahedron. This suggests another way of flattening, Having deformed the sphere into the tetrahedron, we can just cut along these three edges and flatten out like this, giving a flat representation consisting of 4 triangles glued together into a 6-sided polygon. The 6 outside edges are identified in 3 pairs: this white pair, this mid-green pair, and this dark red pair. This new representation of the sphere still contains all the information necessary to reconstruct the original surface, or should I say, the original class of surface. The identification of the edges in pairs specifies the tetrahedron, but that's in the same topological class as the sphere. What about other surfaces? Well, for very complicated surfaces, we might end up with complicated flat polygons with lots of edges. But given any surface, however complicated, we can subdivide it into polygons and flatten them. What we can do then is to apply a computational method to the flat representation in order to classify the surface. The method effectively includes calculating a number for each surface called the Euler characteristic of the surface.
To explain the Euler characteristic, it's easiest to look first at surfaces made up of flat faces, polyhedra, like this cube or this tetrahedron. The Euler characteristic is defined as the number of faces minus the number of edges plus the number of vertices. I'll take the tetrahedron as my example. There are 4 triangular faces, these 3 and this one. Edges, 3 at the bottom and 3 here, 6. And 1, 2, 3, 4 vertices. Total equals 2. So the number 2 is the Euler characteristic of the tetrahedron. Faces minus edges plus vertices. I won't do it for the cube. You can try it for yourself afterwards if you like. What I want to get onto straight away is how we generalize the Euler characteristic to surfaces other than polyhedra. It's very simple. All we do is take a flat representation of our surface and count faces, edges, and vertices in it. For the sphere, we've seen 2 flat representations. Let's try the hexagon first. Well, we've got these 3 interior edges to take into account, as well as the 6 exterior edges. Since we got this by first deforming the sphere into a tetrahedron and then flattening, we expect to get the same answer as for the tetrahedron. And we will, as long as we identify the outside edges correctly. Otherwise, we would be counting them twice. Well, let's see. 4 faces is okay. Now, edges. It looks like we've got 9. 6 outside and 3 inside. But the outside edges have to be identified in pairs. So we've really only got 1, 2, 3 edges on the outside. Therefore, the total is 6. Vertices? Well, it looks like 6 rather than 4. But when the edges get identified, these 3 corners merge into a single vertex. So there's that vertex plus these 3 is 4 again. So the Euler characteristic of the sphere is the same as for the tetrahedron, 2. In a moment, you'll see that for the torus, we don't get the answer 2. But first, there's a loose end to tie up. Remember, each surface can have lots of different flat representations. So for the Euler characteristic to be of any use, we need to be sure that for any particular surface, all its flat representations give the same answer. Well, that's a theorem which we can't prove here, but we can at least check it for our other flat representation of the sphere, which is this one. Number of faces, 1. Number of edges? Well, these 2 edges get identified to a single edge, and these 2 are identified. So this pair constitutes one edge, and this pair a second edge. Vertices, this one on the equator identifies with this one. So that's 1, plus the north and south poles is 3. Total, 2 as before. So that's how we calculate the Euler characteristic for a general surface. We choose any flat representation and use the formula. The importance of the Euler characteristic is that it's a topological invariant. That is, it depends only on the topological class of a surface. So if we calculated it on any surface homeomorphic to the sphere, we would still get the answer 2. Conversely, if we found a surface which gave a different answer from 2, we would know that the surface was not homeomorphic to the sphere. So we should perhaps try it on the other surface we've met, which is a torus. Here's our torus, and we'll use the flat representation we had of it before as a rectangle like this. It has one face, 2 edges, because this pair constitutes a single edge, and this pair a second edge. Vertices, actually all 4 corners constitute a single vertex. You can see that more easily on the cut torus. You see that all the 4 corners have to join up. So there is only one vertex, and the Euler characteristic is 0, 2 less than for the sphere. Again, the number 0 is independent of how I subdivide the torus to make a flat representation. I won't bother going through the computation for a different subdivision, but let me show you one just for interest. This one actually cuts the torus into 6 rectangular faces, which I can flatten. And if you computed the Euler characteristic on it, you would get 0 as before. And that's the important point. The torus has a different Euler characteristic from the sphere, 0 instead of 2. And as I said before, the Euler characteristic is a topological invariant. So whenever you find it's different for 2 surfaces, like the sphere and the torus, you've established that they're in different topological classes.
In fact, the Euler characteristic can do rather more than tell us that 2 surfaces are different. It can tell us how different. In the case of the sphere and the torus, the difference of 2 in the characteristics is a direct consequence of the hole in the torus. To show you why, I'm going to take a sphere with a subdivision on it and convert it into a torus. And you'll see that this reduces the Euler characteristic by 2. I've chosen a subdivision which includes 2 triangular faces opposite one another. And to make this into a torus, I can make a hole in it by first removing these 2 triangles. This leaves 2 triangular boundary curves, which I can then push inwards until the front one meets the back one. And the torus I would get if I did that would have the subdivision you saw earlier. The 2 triangular boundary curves merge to form this inner triangular curve. We lose one triangular curve in going from here to here. And now you can see why constructing a torus hole in the sphere must reduce the Euler characteristic by 2. The first step, removing 2 faces, immediately reduces the Euler characteristic by 2. And in fact, it doesn't change any further when we glue the boundary curves together. That just causes the loss of one triangular curve, which has the same number of edges as vertices, 3 of each. But since edges and vertices are counted with opposite signs, the total isn't affected by the gluing. So the topological difference between the sphere and the torus hole, is precisely captured by the difference of 2 in their Euler characteristics. By the way, I would have got the same thing if I'd performed the joining of the boundary curves differently. If I'd curved these triangular lips outwards instead of inwards and then glued them, I would have got a sphere with a handle. It's a rather deformed sort of torus, but it is still a torus topologically. So its Euler characteristic is still 0, and that's explained in the same way as before. It's the original loss of two faces which reduces the characteristic from 2 to 0.
Well, this last idea takes us into the final item of the program, because it leads towards a classification of surfaces, as follows. We can repeat the process of adding a handle. If we make two more holes, I've made quadrilaterals just for variety, we can curl the boundary curves either inwards or outwards and glue them together. When we do this, we get a second handle, this one here, and it makes this surface topologically distinct from the one-handed surface, and that is reflected by their different Euler characteristics. In fact, the characteristic is reduced by another 2, from 0 to -2, by exactly the same argument. It dropped by 2 from here to here when we removed the two faces, and it remained reduced by 2 when we glued the boundary curves together, because the loss of one quadrilateral means we've lost the same number of edges as vertices, 4 of each. So this construction can produce an infinite number of different topological classes just by adding more and more handles. Each time we add a handle, the Euler characteristic drops by 2, so we get a different topological surface. This infinite list of surfaces actually forms a very large part of the full classification of surfaces, and we've accomplished it using a single topological feature, the Euler characteristic. In fact, the complete classification can be accomplished with just 2 more topological features, that is, topological invariants. We can't cover them in full now, but we'll end the program with a brief word about them. One is the idea of orientability. This idea is actually quite subtle, and we'll cover it in detail in the next program. A surface, however, is either orientable, like the ones you've seen, or it's non-orientable. The final topological invariant is quite simple, and we'll do it now. It's the number of boundary curves which a surface has. For example, if I left this surface with 2 holes, instead of joining the edges together to make a handle, this surface has 2 boundary curves, like these, and it's topologically distinct from the one we began with. Or we could have only 1 boundary curve, and we'd have a different surface again. So in addition to the number of handles, we have to consider the number of boundary curves, 0, 1, 2, 3, and so on. And that completes the topological invariance we need, as it turns out, in order to classify all compact surfaces. We just have to say whether or not the surface is orientable, what its Euler characteristic is, and the number of boundary curves it has.